All right. Share my screen. I believe my screen is being shared. All right. So these functions and packages. Test. Sorry about the noise. So Sunday Gule was talking about t-test. The t-test is a parametric test, hypothesis testing, and there are assumptions you take, you consider. If those assumptions fail, you cannot do a t-test, and you rather go for a real test. What are the assumptions? One is the two data must be independent. Another is that the two samples that possible are normally distributed. You don't have significant outliers, and they are equal variance. But in case where you are testing for unequal variance, you have a Welch two sample t-test to be done in that regard. As you have seen in your practical session, we don't specify because you use your t.test command to do a t-test. So if you don't specify equal.var equals true, so it's going to do a Welch two sample t-test for you. So I guess you don't have a problem with this. This is the command to run a t-test. So as you can see, a t-test is a method of comparing two samples. It can be done to determine whether the samples are different. Now, I've talked about this. Yeah. So this guy, they didn't specify whether equal.var is true, but by default it is set to be false. That's why you have a Welch two sample t-test performed there. And this is your test statistics, calculated value. A Welch two sample t-test usually give you a fractional degree of freedom. That's why you have it to be in decimal, as you can see here. Your p-value is used to make a decision. The decision rule. So decision rule using p-value. You compare the p-value with your level of significance. In this case, the default level of significance, if not specified, is 95%, which means 0.05. We call it alpha. That's what they generally call it, alpha. So 95% is actually 1 minus 95 over 100, which is 0.05. That's the alpha. Now, whenever your p-value is greater than your alpha, you say you fail to reject the null hypothesis, or you say you accept the null hypothesis. Or whenever your p-value is less than alpha, you say you reject the null hypothesis. If you are rejecting the null hypothesis, means you are accepting the alternative hypothesis. And as I said in the last class, that null hypothesis assume equality. Now, in the case of t-test, you say your null hypothesis usually, if you are comparing two samples, you say the mean of sample 1 is not different from the mean of sample 2. In that regard, you can say it that way. Or you can say mu1 is equals to mu2. And your alternative hypothesis can be non-directional or directional. So your alternative hypothesis can be mu1 is greater than mu2, or you say mu1 is less than mu2, or you say mu1 is not equals to mu2. Any which way. I want to specify that you use this, let me see. If you put alternative because it's two-sided, this does a two-sided test. By default, it does this for you. So the default is two-sided. But if you want to perform directional hypothesis testing, you specify alternatives equals to greater to say, okay, if mu1 is greater than mu2 or less in that regard. So, for example, you see this, in this case, the p-value is less than 0.05. So you reject the null hypothesis and accept the fact that the mean of sample 1 is significantly different from the mean of sample 2. So, hold on a minute. Okay. So, I think I've talked about this. So you can see alternative hypothesis, true difference in means is not equal to 0. That is difference between the first sample and the second sample. This one is two-sided. So you specify var dot equals to saying that you are performing a standard t-test. But if you don't specify this to be true, by default it is false. I'm going to do a Welch two-sample t-test, as you can see in this place. I guess Sunday, have I touched the part you need me to touch? Is Sunday still on the call?
Yes, actually, it's actually this place, this all these sample tests. Thank you very much.
So this is what we have for today. Statistical analysis on massive scale using R and map out. So let's try and cover this.
Can I ask just a simple question on this? Okay. Is it possible to do an over test on this on R2?
Yes. ANOVA, and you can use ANOVA to compare the
means of model
between two models.
Okay.
ANOVA.
Okay, no problem. I'll do that. Thank you.
Yep. So statistical analysis on massive scale R and map out. Let's see what the key objectives we want to cover today. So first is understand key requirements for data analysis on massive scale. Install and use R. These you guys are going to do this. You're going to do this on your own. You have the material to do this. If there's any challenge, you can try and solve that. I've not had the luxury of time to. I've been busy anyway. So also perform text mining using R. Understand map out features. This one you might not necessarily, you won't be able to practice this guy. I don't think you'll be able to practice this guy. I've gone through the material. You shouldn't be able to practice this guy, but they made some assumptions and they tried as much as possible to explain the concept anyways. So statistical analysis on a massive scale. Now, when talking about statistical analysis on a massive scale, we're talking about big data, trying to analyze the large volume of data sets you have to analyze the whole of this assets here. Now, before we enter this session, we talked about hypothesis testing. And hypothesis testing, basically, you generalize based on the sample. You generalize based on the sample. So you have this big data somewhere, but you don't have the computing power to perform statistical analysis on this data. But you can just pick the significant sample from the population and do your own analysis on it and come to a conclusion that you can generalize. You do that a lot in mathematics too. You do that a lot in mathematics. I don't know whether some of you know what we call something proving by induction. We call something like induction, mathematical induction in mathematics. I don't know whether some of you know that.
Yeah.
So what you do in induction is that you have to put something to let me go to that. You want to put something, maybe something like this. say don't mind me, I have to talk about mathematics. I know some of you don't like mathematics. Let's say Oluwatobi, I don't know. No, don't let me. Sorry, I didn't say that. I didn't say that. So where is the marker? Okay, okay. So let me erase. So maybe you have to do something like this. You know, you have let's say one proof that 2 raised power n is always greater or equals to 2n for n greater or equals to 0. Yeah, I want to do this. Now, this is what mathematical induction does for you. Yeah. So for n greater or equals to 0, n is a natural number. Let me say n is in n. Now, n is in n. Now, there are infinite number of natural numbers starting from I should have put 0 there, but 0 is also true for this case. I should have put 0. So don't let me put n. Don't let me put this. So let me put a z plus. So now what mathematical induction does is that you cannot prove everything. You cannot say, okay, z plus now, let's include 0 now. You can, if you prove for 0 now, okay, you find that 0 is true. Prove for 1 is true. Prove for 2. If you want to do it that way, you continue proving till 1 million, till trillion. You cannot keep doing that. So what it does is that, okay, you can say, okay, let me prove from 0. Let me prove for 1. I can look at, let me prove for 2. Let me prove for, though in mathematical induction you prove for the base case, then what mathematical induction does, you prove for the base case. What's the base case here? You're starting from 0. You prove for 0. After you're proving that for 0, this case is true, you prove for a particular integer, say k is going to be a positive integer anyways. Then you are going to assume this. You are going to assume that the case is true for this guy. You are going to assume. So after you made the assumption for this guy, then you are not going to prove that it is true for this case, k plus additional 1. So for the, you put that you assume that it's true for the kth term, then you now prove that it is true for k plus 1 term. So if you put 0, you already have 1. If you put 0, you have 0. 1 is greater or equals to 0. It is true. Okay, I can be curious. Let me put for 1. If I put 1 here, 2 per 1 is 2. If I put 1 here, 2 times 1 is 2. 2 is greater or equals to 2. Yes, it is true. Okay, I can be curious again. Okay, let me do for the next number. 2 is per 2, 4. 2 times 2, 4. Is still greater or equals to, is this the same? I'm not satisfied. Let me put for 3. 2 is per 3, 8. 2 times 3 is 6. 8 is greater or equals to 6. Okay. I think it's true for all this time. Okay. Let me now say it is, let's say assume that for some k, is, you say k is, can say k is anyway. Okay, let's assume it is true for some k. You now say 2 raised per k is greater or equals to 2 times k. You assume this. So you assume this. So after you assume this, then you now go further. Okay, to prove for either it is true for the next term, which is k plus 1. So if you can prove this case, so you want to prove this case, it has to conform to something like this. So you have to manipulate your way and get to something like this, and you generalize, oh, this case is actually true for all n greater or equal to 0. No, you didn't prove for everything, you didn't prove for everything, but you have come to a conviction that this case is actually true. So that's how null hypothesis is. If you can find a significant sample of the population that represents, that is a true representative of the population, you can generalize. But then it is very difficult to find a sample that is a true representation of the whole population. So it can be biased. Your results can be biased because of outliers and less of them, and your analysis is going to be faulty somewhere. So that's why we need to do big data. That's why you need to do big data. If you can now work on all the data you have, that you can work on them, you can process everything, then you can be more confident about your results than taking just sample of a data set. So let's say, for example, now for someone that sells umbrella now, now from let's take Nigeria for a case study now. Let's say from January, from January to let's say maybe April, it's not most likely to rain. It's not most, and then let's say September to December too. It's not most likely to rain. Now you have a data. Let's now say you are trying to predict this. You're trying to predict the sales of umbrella of the sales of a particular retail store that sells umbrella with the data you have, and the data is so large, and you decide to pick a sample, and your sample actually picked from September. Now the sample picked from September to April without capturing May, let's say May to July or August. Now this analysis is going to be biased because you are going to assume that, oh, again, if you stay too long in this space, you won't make enough profit because this umbrella business is not moving. But if someone should take note of data in this space, you notice that the sales of umbrella in this month is going to be relatively higher than in this month, because this month it doesn't really rain in this month, but this month, the month where it actually rains like that you know that rain will most likely fall in this rain. So people who are let me get umbrella. We enter the rainy season and start raining. And in this month, the person will experience spike in sales and less like that. So that's why having to use take sample from a population to and make analysis and come to the results can be biased to some extent. So to pick a significant sample from a population is usually the most difficult part to do. But if you can get that significant sample, then you can generalize for the whole population and be confident that, oh, it is confidence interval within this. I'm confident that, okay, in months May to July, this person is going to sell like 300 umbrellas to 400 umbrellas. So you can make some kind of prediction on that if you have a significant sample. But generally that significant sample from population is generally challenge. So that's why you have to take statistical analysis on a massive scale. So let's see the amount of data that is traditionally processed by typical statistical analysis tools and systems earlier used to be in the range of 10 and hundreds of gigabytes compared to terabytes and petabytes, which is considered as big data. So often traditional analysis required an expensive symmetric multiprocessing machine with huge memory to hold the data being analyzed. In those days, you have to have your data in memory. You have to work on your data in memory. So talk about how, talk about SPSS and the rest of it. So let's say how, for example, you have to have your data on the local system you're working on. Now, your local system, let's say with my system now, it has the limits to what it can take. Just like maybe your flash drive or your hard drive. Maybe you can have a flash drive of 64 gigabytes. It means that your flash drive cannot take anything that is above 64 gigabytes. So it means you cannot take anything above 64 gigabytes. So if you want to process everything, you have a data that is like 100 gigabytes, there's no way you can process that kind of data. So you have to pick some part of the data and try and generalize for the whole population. So that's the challenge then. So the reason behind this is that many analytic algorithms were quite complete complexity and were designed to run in memory as they require multiple and often frequent passes through the data. So the most efficient way of running is actually in memory if you have the stock in somewhere. Just like I'm in the office now. It's flexible for me to collect something. It's just someone that is just beside me here than me to go out and go and pick it up from someone in the other office. So it reduces latency, you know what. So let's see the next verse. Sampling technique as a solution. So since such hardware was not only expensive but also time consuming, so analysts began working on only a sample of the data. So the idea was to use only a statistically significant sampling of data from the huge data repositories to take to statistical aging and work on it. So finding that statistically significant sampling can be challenging for sparse or skewed data sets, which are quite common. So the scale on which analysis requires to be done is depending on various factors and complications. So this is going to be the challenge. That's statistically significant sample. To find it's usually a challenge. So it might include the volume of data in which analysis is done. These factors and complications include the following: the number of transformations required on the data set before applying statistical models. So like if you check the last class, I said last class, the currency class we did, we tried to build a time series model for Bitcoin data sets. I don't know, maybe some of you know it's cryptocurrency. So it changes over time, even in seconds. It's a real-time data. So, but we had an aggregated data for a day. So like opening price for a day, the closing price, the highest price the currency went, and the lowest of it. So okay, you can aggregate this guy and say take the average of all those prices and try to do build a time series predictive model with that. But generating our results, we couldn't build a very, very nice predictive model because it doesn't really perform very well. For you to come to build a very good model with that kind of data set, you have to do a lot of transformation to make to stationarize your data. So those number of transformations required on the data set for applying statistical models, the number of pairwise correlation needed to calculate. You know, for example, by building a regression model, So you most likely would like to put independent variables or predictor variables that are highly correlated with your dependent variable. So you can do pairwise correlation needed to calculate the degree of complexity of the statistical computations. you have to do some statistical computing, maybe ANOVA, uh, maybe standardization, normality, and all of that. So it depends on the kind of model you want to build, the number of statistical models to be applied to the data set. So these are factors to consider when doing sampling. Now, so Hadoop as a solution to having to run statistical analysis on a massive scale. So Hadoop provides a solution to the problem of performing analysis on massive scale by providing a platform to perform MPP computations on data. So I guess before this, guys, we've talked about Hadoop ecosystem. So I think you guys have been put through the Hadoop environment. Talk about why mapping is a solution for parallel processing of two data sets on Hadoop, converting statistical model to run in parallel using MapReduce. I know using MapReduce is not easy. So basically, MapReduce is used for text mining, less of them, which can be used for sentimental analysis and all that. So it runs it's provides a solution for parallel processing of new data on Hadoop, which is actually a nice uh, solution because so what it does is that, okay, you have mapper, you have the reducer. So the mapper like split the jobs and give it to different workers which works on it. Then you have the reducer that compiles the results, first shuffles them, reduce it to a single output, depending on what you want to do. So not many analysts or statisticians will be able to handle this MapReduce program efficiently because I think MapReduce is built with Java. You have to not so many people know Java. Even statisticians, it is very rare a statistician that you see that actually does Java. So it's quite rare. So as a result, Hadoop developers keep working on solutions for implementing the algorithms required to perform statistical modeling and analysis without overburdening the analysis with knowledge of parallel processing. So people, statisticians and analysts, they use software like R, SAS, SPSS, and the likes of them. So its integration of R language is Hadoop or R Hadoop. MARHouse is multiple statistical models and library functions. These are tools that have been implemented that can help statisticians even build their own MapReduce jobs without having to write Java code. So that is going to reduce the burden on the statistician, which is a very good thing. Okay, to do a recap on Hadoop, but we talked about Hadoop for this class. So Hadoop is an open source software application that provides distributed storage and computation capabilities for processing large amount of data. It is based on Hadoop distributed file system and allows users to program parallel execution programs on a group of computers, also known as Hadoop cluster. So you have the HDFS. The main components is HDFS and MapReduce, and before Yarn was introduced. For Yarn, so the first version of Hadoop had just HDFS and MapReduce. Now, before Yarn was introduced, because then you just have to write everything in Java, and it wasn't that flexible. It wasn't that flexible. So Yarn was introduced yet another resource negotiation that allows other applications to run. You can run SQL query. You don't know MapReduce, you can run SQL query. You can write scripts and the likes of them. It's actually nice thing. So the HDFS component contains nameload and the data load. So this is the main storage of Hadoop. So what nameload does is keep records of the data nodes on Pipedrive to manage data nodes. It has this metadata. So we know that metadata is data You can say data of data or data about data. So um it's just like now. Okay, first of all, let me ask you guys. Let me ask you guys. What is the metadata and give me an example. If I should ask you what is the metadata and give me an example, will you please tell me that? Someone that wants to hint us on that. Hello.
Sorry, I didn't get the question, please.
Yeah, what's the metadata? And can you give us an illustration of what the metadata is? Is anyone in this class?
Hello.
Yeah, I can hear you. Is that able to hear me?
Is is
Okay.
data that contains information about another data somewhere. Basically, contains an information. An example basically is maybe you have a particular audio file, like a song, and then the metadata is like the information about the album name, the artist name, and something like that. So that's an instance. Metadata simply contains information about another data that you have somewhere else.
Okay. Okay. I think yeah, yeah.
Metadata is can I say something? So, metadata is
Okay.
like your data dictionary. You know, when you have a
Mhm.
data set and you have a dictionary that describes data you have.
Yeah, yeah, you can say that. You can
Yes.
say that. Yeah. So beautiful, beautiful. So data contains blocks of files and communicates with other data to manage file read and write options. But I want to ask you a question on the HDFS. Now, how does HDFS read and write works? So, so can you just I just need one key thing that you tell me. I'm just looking for one key thing you tell me. So HDFS, how does it read and write file? Can someone explain that to us? I'm listening now. Sorry, I was not on mute. I didn't unmute myself. You guys, please, can you explain how HDFS does use their writing now too? Adito, can you please help us out with the question if you guys are not there?
Mr. Emmanuel.
I can hear
Mr.
you.
Yeah, I don't really know how exactly to answer that particular question, but I'll just say what I don't know what I know. I know that the HDFS is made up of two major components. That's the data node and the name node. So they work on like a master slave kind of level where um, I think I think the name node is like the master, and then the data node works on the on the data. Anyways, so the reading and writing is either going to be conducted by either of these. I don't think I really, you know what, I don't think I want to attempt this question. I'm sorry, but I really cannot specify how that happens. Because I usually just picture the HDFS as like just a storage system, mostly for sorting files and setting files, appropriately. So I don't really know how reading and writing would work on that, because I don't know. I think you would have to help us with that, Mr. Emmanuel.
I guess everybody just stay on mute. It's really serious. It's really serious. Hey, God, the wish you must. God, the wish. I'll leave you guys to that. I'll leave you guys to that assignment. I will say.
No, please, can you not do that right now? Can you just tell us, please? Please.
Don't worry, I'll just do the assignment. Maybe you guys don't have anything. If you don't have anything to the next assignment, we'll talk about it. So, we have the map which provides a batch-based distributed computing environment for the Adobe platform. So it performs parallel processing on large amounts of raw data, such as data from social network, relational data from databases. You can do that also. And data generated from interactions on the internet. So basically, that's what I've said so far. It just is mappings for text mining, only sentimental analysis. You can do that with databases, relational databases. You can have a database that you can have social network data that has been constructed in the structured format where you can access it. Then you can run a map with this job using you incorporated R with MapReduce. I think you should be able to see that as we move on to the next slide. So I think you know this last part. MapReduce processes a job by dividing it into small, which is the work of the mapping, value map functions, and reduce functions. Then reduce just gather those information that we worked on by the workers, then compile it to a single output as you have specified. So integrating R and Hadoop, which you call R Hadoop conjunction. So it's the approach of integrating R and Hadoop, an open source project that allows programmers to define their own map and reduce functions, and they actually use the functionality of map reduce in R. So there's a function map reduce in R, but you have to install some packages and do some stuff in the can run R on the Hadoop platform, write R queries to access files on the DFS. So Hadoop allows programmers to make use of all full features and existing environments of R and leverage the Hadoop platform. So we have packages like this. R is DFS, which enables you to access the distributed file system of Hadoop, and RHBase, which enables to access the database part of Hadoop, and the RMR2, which allows you to write your own map reduce jobs in R. So to install R, we first need to install certain R packages as follows. So in your manual, you are going to see something like this. There you should see a step-by-step guide of like a screenshot of how it's going to look like an algorithm. I think you have to do it. Sometimes you have to log into Hadoop. I think on Hadoop you are going to do all of this. Then there's a point in time you are going to set your environment in HD user. You just have to just log into HD user and set up environment and less of that. So you are asked this question. You are using R Hadoop to process a large amount of data stored in tables. To manipulate this data, which of the following R Hadoop packages will you use? So A, RHDFS, B, RHBase, C, RMR. Sense basically the same. So between these three, what's going to be our answer? So an open question. It's an open question. What's going to be our answer?
I think RH base, because RH base normally is used to manipulate data, data. It's just like SQL or Hadoop. That's no, I know SQL. I know SQL is used for transformation of your data. So to manipulate data,
Okay, so that's a contradictory suggestion or answer. But I want to support Iola with that answer. Oh, I go with Iola. I'm looking for one more person, maybe to support or oppose the answer.
Yeah, I support.
Okay, yeah, that's absolutely correct. You use RH base. So, you are going to describe the integration of R with the Hadoop platform. Also list some advantages of R Hadoop platform over R. So let's think about this part. So, okay, what advantage can you say about this having R Hadoop the R Hadoop platform over the R itself? So what major advantage can it?
How Hadoop provides massively parallel processing capability to enable you to process large amounts of data.
Okay, yeah, that's absolutely correct. So let's see the next slide. Now, text mining for deriving useful information. So text mining is a set of techniques and methods used for automatically processing natural language text available in large quantities. So this text can be in form of computer files. The aim of text mining is to extract and structure the text for quick, non-literary examples. So in order to discover even data for automatic decision, so you can text mining is you can try to can do that with you can do social media analytics and like let's say Twitter for example, you can analyze tweets of people on a particular product and try and because the opinion mining, try and or sentimental analysis and try and you can know the public's opinion of a particular person or a particular product. So text mining is different from telemetry, but that's much in common with telemetry. Telemetry is just trying to find style of writing a particular article or something like that, or to try and know the author of that of a particular book. It's an extension of lexicometry using advanced methods of multidimensional statistics. So you can say schematically text mining is lexicometry plus data mining. So trying to find structure of text data mining, try and generate insight from data, in this case form of text. So you can also visualize. There's a command in R that I can use to visualize words. I think I forgot, it's like a visualization command. I think it's words. If you want to do plots, you say plot into bracket. Then you want to draw a line, say lines into bracket. I think in this case, I think it's words. So you can try and see the words that are almost in particular text. After you've done your text mining, then you want to visualize the word that are almost. So the word that are almost, it will be bigger compared to some words. So it's just like a kind of bubble chart. Actually nice. So let's go to the next slide. So what's the text mining process? First of all, structuring input text. So you might need to structure your input text. So what you would like to stick together, what you would like to be separate. I now want to add language rules. Okay. So adding language rules. Maybe kind of adjective clause, verbal clause, what you really want to see. Removing useless terms might not necessarily need sometimes, maybe PHP, maybe a something. Now not necessarily need some words. Inserting structured data into the database. So maybe after you have structured data, you want to use the database. Then after you've done that, you might try to identify patterns in the stored data. You use mostly use visualization to do this. Then analyzing patterns, then generating information to find out results of it. So one of the common application of R is text mining. So you have a package in RTN, text mining, used for text mining. Okay. So this package contains about 50 new articles with additional metadata information from an extensive markup language dataset. So you have some packages in R that comes with data sets. Like there's a library in R, like a mass. It comes with a data set called survey. I think if you have practiced your lab, you should have come about that. So you have some packages in R that comes with that data set. So I guess the time series, the package that imports the time series command also have its own data set. So that's when you now have these air passengers and the rest of it. So the purpose of that is to be able to explore the functions of those packages. So this package is developed to work with plain text, articles, papers, surveys, and web in form of HTML, XML, and SQL. Okay, we talked about this. So now you'll be able to talk about R and R2. So this slide does not really you have to go back to your material and read in details. So my out is an open source project of Apache, open Java libraries for distributed or otherwise scalable machine learning algorithms where you can do collaborative filtering, machine learning, like classification, clustering, and all that. So these are called quick machine learning techniques as classification, clustering, association, rule analysis, and recommendations. So classification, I think, is just to separate into separate buckets based on particular rule as specified by the analyst. Like there's these reports we used to dish out to clients, one of our clients we're working with. So we do this what we call it RGS analysis. So the aim of this analysis is to classify customers into specific buckets. There's 6 buckets. So we call them, we give them labels called RGS 0 to 7. We have RGS 8 to 30. We have RGS 31 to 60. Then we have RGS 61 to 90. Then we have RGS 91 to 180. Then we have RGS 181 to 365. So the thing is this, okay, the one of RGS 0 to 7 are those customers that have transacted within 7 days, that have transacted in less than 7 days. So if you transacted yesterday, you'll be in RGS 0 to 7. If you transacted today, you'll be in RGS 0 to 7. Within 7 days, you'll be in. So it means you are checking the last time you actually transacted. So the last time you transacted was 9 days ago. So you're going to fall into the bucket of RGS 8 to 30. And this classification might be kind of, I don't know, might be kind of biased, or I'm looking for one English to use. I'm kind of biased, or let me say biased. So let me give you an illustration. Let me give you an illustration. Now, it's possible you have a customer that the last time the person transacted is today or yesterday. But if you check the previous transaction after the one he did today, it can be maybe the last 60 days or the last 90 days. Now, so because that person, the last time the person transacted was yesterday or today, you say the person is between 0 to 7 RGS, and the person is transacting customer. Maybe that transaction was just by chance. Maybe someone just sent that person money and maybe give away or something. Person just used it, you know. So you consider that person to be transacting, whereas that person is not actually transacting. And maybe someone that is in RGS 8 to 30 now, maybe the person transacted in the last 8 days. But between that last 8 days and 30 days, the person has done as many transactions as 50. I would say 31 to 60. The person transacted as many times as possible, but maybe due to some business, the person was not able to transact. So you consider that person that person, you now be sending promotional message to that person that, oh, about transact. Whereas there's a person that actually transacted yesterday that was just by chance, and the person is not really transacting. You understand? So though classification can be biased in some cases, but it's rare. It's rare. You can't actually capture everything. Clustering is just trying to group some people based on some kind of property they have, and trying to like segment them. Okay, this person belongs to this group and all the rest of them. On the rest of them. So let's move. So map out can run independently, but it's also implements map practice paradigm. So it works with Hadoop and can perform machine learning over large data sets on Hadoop. Although map My libraries are designed to work with an Apache Hadoop context. They are also compatible with any system supporting the marketplace framework. So, I said there are three main categories of math algorithms for supporting classical analysis. You have collaborative filtering, clustering, and classification. Now, collaborative filtering can is just trying to probably identify maybe it can be buying pattern of a particular customer and you can try to generalize, or you can try to advise a particular customer, recommend product to a particular customer based on the buying pattern of another customer. So it's like something like this. Maybe Iola came to let's say ShopRite. Now Iola bought bread, and the next thing Iola bought is sardine. And afterwards, Iola now bought chocolates. Now this is Iola. Now another person can come another time and person bought bread, and the next thing the person bought was sardine. And based on that buying pattern of that person, I'm like, there's a guy that bought something this kind of pattern, and the site can just recommend, okay, we like to buy chocolate, something like that. So you have this recommendation engine also works in like of YouTube. Let's use YouTube as an example. Now, if you go to YouTube now, there's a time I was watching something on YouTube. So most of the time I watch those times I used to watch football highlights. I'm a Chelsea fan, so I used to watch Chelsea highlights and lots of them. So I don't know. There was a time I was just like, after I finished watching a particular video, so the next video that was going to come up, you just see something like the best goal Drogba scored. The top 20 goals for Chelsea. So if you see stuff like that, before you know it, your data has been exhausted. If you are someone that likes comedy, before you finish one particular video, they will recommend another comedy for you. Without you even telling them there's comedy things you want. They will recommend based on the kind of things you watch. You see stuff coming to your playlist. Then by the time before you know, you have finished your data. So those are stuff you use for as a marketing strategy and to drive business decisions and less of them. So let's look at the MAG deployment over the Hadoop framework. So you have this collaborative feature clustering and classification. So you can also use create a user-defined algorithm. Then it works on Mac videos as we said earlier. Then it has the analysis source manager. Then it's based on the Hadoop distributed file system. So collaborative filtering. So my was specifically designed to serve as a recommendation engine. It uses a collaborative filtering algorithm. So it also combines multiple clustering and classification algorithms to create more accurate recommendation based on input data. So you stream YouTube a lot, and if those of the things you do is watch football highlights, then watch comedy, then watch Yoruba movie. By the time you just click on YouTube, if you should enter by the time you log into YouTube, the whole thing you'll be seeing, like the first 20 is football highlights, maybe of your favorite club, comedy, and what was that name? Comedy and Yoruba. They will give you the list latest one in town. You'll be seeing it there. So if you are someone that usually, and then you go to YouTube, you see latest Yoruba, before you you're able to complete it yourself. Then so you just make life easy for you. Like to access the data to make it your platform. So the recommendations can be applied against user preferences, taking into consideration the behavior of the user. So by comparing a user's previous selection to send to find the nearest neighbor has the similar decision history and the next. Okay. So you have clustering. This is a form of unsupervised learning where the labels or data points are unknown ahead of time and must be concluded from the data without human input, which is the supervised part. So objects with the same cluster should be similar, but objects from different cluster should be similar. So the model, after you build the model, and the model is so that the model is working perfectly well. So if the model should receive any input, any additional new data point, you should be able to tell, okay, this particular data point belongs to this cluster. We have like 3 clusters, so okay, this belongs to cluster 3 and all data. So choices made beforehand regarding the number of clusters to be generated, criteria for measuring similarity and representation of objects will play a role in the classification which occurs as a result of applied clustering algorithms. So the number of clusters depends. So let's say, I don't know, something that will come to my head. So I'm trying to. So you might have maybe the scores of some students now, and you're like, oh, A from 0 to 100 now. So you like want to separate them to different cluster. Then you have if you say 3 cluster, like this now. So it means you can have something like good, fair, or poor. But if you specify 2 clusters now, it seems like going to have something like good or bad. If you specify 4 clusters, you can have something like excellent, good, fair, or poor. Now it depends on the number of clusters you specify, and they are going to depend on the result you're going to have. So if you specify 2 clusters, so good or bad, now it depends on the data points. So if you have the data point has something like between 60 to 100, then you have something like 40 to 0. So those in 60 to 100 will be in one cluster. Then those from 0 to 40 will be in a separate cluster. So depending on the range of values you have. So if you have 3 clusters, prefer 3 clusters, which means you can have something like maybe 70 to 100, then maybe 40 to 0, then maybe 41 to 69. So it depends on the number of clusters specified beforehand. Also, classification algorithm use human label training dataset where the categorization and classification of all future output is ruled by these known labels. So that is example of what I give the I'm talking about RGS. So the RGS, this is how it works again. So if I should run that, if I create a procedure called RGS now, so if I want to determine the RGS for today, RGS for today is going to go based on today's date. It's going to use the system date. Okay, as at this time T, it is the base case for every customer. Now, if a particular customer transacted, today is 14th of August. So if someone transacted on the last time they transacted is 10th of August. So you just do what is the difference between what's the date difference between today and 10th of August? Okay, and it's 4 days. So 4 days is between 0 and 7 days. So okay, this person is RGS 0 to 7. Now, if that first the date the person transacted was 1st of August. Now all the 14th of August and 1st of August, okay, 13 days. Okay, the person falls between RGS 8 to 13. So it's based on those rules you have laid down. That's how the classification is going to work. So this classifier is used to concept of supervised learning. Classification is set by the training data has been labeled previously by domain experts are applied against raw processes that find out their appropriate label. So classification is often applied by email services which try to segregate spam email before this landing in our inbox. No. So there's this. So there's sometimes if some emails enter your inbox, that's easy. Let me show you the email like this now. If I go, this is my email, for example, now. If I go to my spam folder, so there's this settings. This is my spam folder. Some are in spam folder, while some you find it in inbox, some social, some promotions. So there's this kind of settings that's been set by Google or Microsoft or the likes of them. Now, if you receive, there's kind of email you receive automatically. If Google just sees scan through that email, oh, this email is not kind of email that's supposed to be in the inbox, then the email goes to your spam folder. So if those kind of email comes in, Google will just direct that kind of email to the spam folder. It's considered that it's not important. It's not something you have to see. So you just try to segregate anything that can just enter into your inbox, unless your inbox is going to be jam-packed with a lot of things. So it's just equivalent as spam, and just lands in the spam folder or your junk folder. So an email containing a set of words or phrases understood to commonly occur in a certain class of spam mail and delivered from an address belonging to a known botnet. Because when you can fairly incorrectly label and identify the email as harmful. So depending, okay, if you should find this kind of phrase in a particular mail, oh, this image should it's not something that you enter your inbox, just go to the spam folder and less of them. So it's so sometimes if you log into your mail and after you check your inbox, check your spam folder, there might be some important information you have in your spam folder, and because it needs to see your inbox and you need to check the spam then. So that's why you send email to 10 people, for example. Now, let's say whether you copy them, whether you copy them or something. Some will see the email in their inbox, while some people they will not see it. It's going to be inside their spam folder. It depends on the classification that was based on the particular platform. So my artwork is you have SaaS, SPSS, and most other task analysis applications include powerful tools for generating workflows. So most of these tools have intuitive GUI that make data generation possible. So mouse gives us enables generation of statistical analysis workflows. You can import human readable format, JSON, CSV, or use tools such as Tableau Desktop. So JSON format is kind of format that it can take anything, so that structured kind of data, just pack everything there. It's just like our organ. Our organ can take in anything. Smart architecture sits on top of the Azure platform, as you have seen in the previous slide. So Hadoop onboarding the programmer by separating the task of programming map reduce job from complex if needed to manage parallelism. So it's onboarding the analyst having to write Java code to build map reduce job. In the same spirit, Smart provides programmer-friendly abstractions of complex statistical program algorithms for implementation because you have libraries whereby you can work with. So, what are the points to remember we've talked about so far? So, R is an approach for integrating R and Hadoop. It's an open source project that allows programs to define their own map and reduce functions. So the R Hadoop includes these three packages. It's very key. R8 access to allows you to access the distributed file system of Hadoop. Then R8 base which enables access the tables in Hadoop in the 8 base. Then RMR2 package that allows you to write your own map reduce. The RMR2 package creates the client-side environment for map reduce to execute the map and reduce functions. So in your material, you are going to see a section whereby they wrote a map and reduce function. So you can specify, okay, this is how my mapper should behave, and this is what my reducer should do. Text mining is a set of techniques and methods used for automatically processing natural language text available in large quantities. Had it been that part was there, we have been able to go through it together. So we've talked about the typical text mining processes. We start from categorizing the text, then try to clustering the text, extracting concepts and relationship, generating taxonomies, performing sentiment analysis, summarizing documents, modeling entity relationship. So, no, this is not the way they categorize this in previous slides. I think it's basically the same. So one of the common applications of RD is text mining. And we have a TM package that is used for text mining. So the three categories of Miles algorithms is collaborative filtering, clustering, and classification. I think that's basically all for this class. Yeah. So I don't
So I have
know.
a question.
Okay.
Is Mahout R based or is Java based? Like programming, the language you use.
What did you say?
Mahout is Java based. Just want to confirm.
My out.
Yes, sorry, I'm calling Mahout. Mahout Java based.
Yes.
So like it's like you know Java, you cannot use Mahout.
I didn't get it. What did you say?
Okay, don't worry, you've confirmed my question. Thank you.
Okay. All right. I think we have 30 minutes of time. Maybe somebody have something might have to go back to and talk about. You have this time to do that. Or I should show you guys that IGS script. I would like to see. Yeah, must. What do we do? Should we end the class now?
Yeah.
Okay, one other person to support that motion.
Yes, I just like to know what no problem. Why is Abisola now around?
Sorry, I didn't get what you said.
Okay, I said I would just like to know what no problem. Why is Abisola now around?
No, there's no problem. It's just in the meeting. The chat.
Okay. Hope she'll be around on Monday.
Hopefully, yeah.
All right, thank you.
Emmanuel, just to ask
Okay.
you, in choosing histogram beans for histogram, that's bricks for histogram, how do we optimize choosing bricks for histogram? Because I know the number of bricks you choose can actually give you a wrong distribution. I don't know how to put it.
So before
A,
that, sorry to cut you short. So if you terminal, you can exit the class if you are not interested in the class. I'm not holding anyone captive or something. So you can continue. I can hear you, Yoga.
is okay. What I said is there a way to optimize number of beans you choose, number of bricks you choose for an histogram? Or is there any rule for choosing beans in histogram or bricks in histogram? Because I know in histogram plot is very, very necessary in looking at how distribution of your data, how skewed your data is. I don't know if you get
Yeah.
my question, sir.
If I get what you are saying, it depends. If you want to, there's a way. If you want to plot your histogram, it starts from a particular point. I can't really, if you start from a particular point and it might not really catch some specific point. So I think the way you can optimize that is to check your minimum and maximum value in that column so that you can specify where your histogram should start from so that it can pick those extreme values. Yeah.
Okay. Okay, thank you. Thank you.
You are welcome. Anybody with another question or anybody want to support Terminus motion that we should end the class right?